In this trigonometry video, we're going to take a closer look at a few more angle identities and how we can apply them to some of the things that we've been trying to do. Now, the first two sets of angle identities are called the negative angle identities and the cofunction identities. These two identities are actually built into the unit circle that we've been using as a resource to do some of our solving. I'll start with the negative angle identities. If you pick an angle that's negative on your unit circle, for instance, if we would go to the sine of negative 30 degrees, and you compare that to the sine of 30 degrees and change the sign, you're going to find that these two have the same value. Or if we're at negative 60 degrees and we look at the cosine value, that's the same as the cosine value at 60 degrees. Those are things that are built into our unit circle, and we tend to use our unit circle more than trying to use some of these identities. But we do tend to use them or have access to them if we do verification. The cofunction identities are also built in. We've talked about this when we built our unit circle, but this pi over 2 is 90 degrees. So we're going to stick to the first quadrant just to discuss this. But if I look at something that's in the first quadrant, something like 30 degrees, and I look at cosine of 30 degrees, if I take 90 minus that 30 degrees, I have sine of 60 degrees. So this cofunction identity says the sine of 60 degrees and the cosine of 30 degrees are the same thing. It says the same thing for cosine and sine here, and it has that similar relationship here for tangent and cotangent. And it applies to all the angles, not just the ones that are on my unit circle. So if I would have a sine of 10 degrees, that would be the same as the cosine of 80 degrees, because 10 and 80 add up to 90. Or if I had something like the sine of 5 degrees, or I'll say the cotangent of 5 degrees, that would be the same as the tangent of 85 degrees. These are also inherently built in to our unit circles. But again, they do come in handy when we talk about verifications. So let's take a revisit of verification real briefly and apply a couple of these. Remember, when we verify, we don't have an equal sign here, so we're trying to make these look the same. And this sine function here is really close to this cofunction identity. Not exactly, but really close. So I'm going to rewrite it, and I'm going to take a negative out. And what that does is it takes the theta minus pi over 2 and changes the signs. So essentially I have pi over 2 minus theta now in the parentheses. And that's what I want. And I have sine of that. I'm going to take this negative 1 and I'm going to keep moving him all the way out to the front. Now, by definition, sine of pi over 2 minus theta is cosine, so this gets written as cosine, except we have a minus sign in front, and that's exactly what they were looking for on the other side. I have a second one up here. This one deals with a cosecant, and you'll notice that there's no cosecant up there, but if we remember our reciprocal trig functions, or identities, I can flip this over and write it as 1 over sine. I'm going to take out a negative again, so these turn around, just like I did in the previous problem. And that negative is going to go all the way in front. So I have something like this. We know that sine of pi over 2 minus theta is cosine. I just happen to have this negative on the bottom, so I have 1 over negative cosine of theta. If I flip that back over, that by definition is secant. So we can use these in verifications. We can also use these when we do some solving. So here I'm looking for something on my unit circle. 0 to 2 pi is just 1 period's worth, 1 revolution around my unit circle. And this is what they want me to solve. This gets kind of complicated in here, so I'm going to replace this with cosine. So I have something like sine and cosine. Now, some of you are going to tackle this right away. You'll go to your unit circle and look for when sine and cosine are the same. Happens at 45 degrees, happens at 225. if I'm talking unit circle, pi over 4, and 7 pi over 4. Now, I could finish solving this. I could divide by cosine, so all my trig functions are over here. So I'm actually looking for a tangent value that's 1. So I could use my calculator, I can use my unit circle and look for an angle that has a tangent of 1. And I'm still going to find it at 45 degrees and 225, or pi over 4 and 7 pi over 4, those angles. So that's how we apply these, how we use these identities for verification and for solving. The other two sets of identities that I included here are the angle difference and the angle sum. We do have limitations to our unit circle. We talk about 30, 60, 90 triangles, we talk about 45, 45, 90 triangles, which are all represented on the unit circle. But we don't have values like 80 degrees, 75 degrees, 110 degrees, so we have to have a way of getting there. And that's what these two sets of identities do. Obviously, there's a lot here to take in, but you have access to these and you can freely use those identities. So the first thing I want to do is I want to find something that's too small. It's not listed on my unit circle. It's in between 0 and 30. I'm looking for the cosine of 15. So I need to come up with a couple of angles that I can either add to get 15, or in this case, subtract to get 15, but I'm going to choose angles that are on my unit circle. So I'm going to rewrite this as cosine of 45 degrees minus 30 degrees. So that's how I get to my 15 degrees that I'm trying to find here. Now, if I go over here to the difference identities and I go down to cosine, this is what I have written. This is what they say to do. So I'm supposed to take the cosine of the first angle, 45 degrees, times the cosine of the second angle, 30 degrees, and I'm supposed to add the sine of 45 degrees times the sine of 30 degrees. So I'm just following that formula. I know these, they're on my unit circle, square root of 2 over 2, square root of 3 over 2, square root of 2 over 2, 1/2. If I do a little simplifying here, I get the square root of 6 over 4, I get square root of 2 over 4, so I can put those together and I can get the square root of 6 plus the square root of 2 all over 4. That's the exact answer for the cosine of 15. The sine of 15 sets up the same way, and you don't have to use this one. There are other possibilities out there. I could take 60 minus 45. I would get to the same thing. I can pick about anything on my unit circle that subtracts to 15 and it would work. It would give me the same answer. I'm going to stick with the same one. I'm going to use those same two angles. They're the first ones I find on my unit circle. And as I follow through on that difference of sine values, it says I'm supposed to take the sine of 45 times the cosine of 30. This one's a minus cosine of 45 sine of 30. So I'm using a lot of the same values here. Square root of 2 over 2, the cosine of 30, square root of 3 over 2. But this time I have a minus sign in between, so my answer looks very similar, except it's square root of 6 minus the square root of 2 over 4. That's the exact value for the sine of 15. And they'll turn this around. They'll give you this version of it and understand that I can put those values together. So if I had an 80 and a 10 and an 80 and a 10, I could put those together and we're really looking at 90 degrees. Or if they had a 20 and a 25 and a 20 and a 25, we're really looking at a 45 degree angle. So they work both ways. I can rewrite a difference like this, or I can take something that's in this form and write it as a difference. So now let's take a look at a sum. Something that's a little bigger. I've got sine of 105 degrees. That's in between 90 and 120, so I have to find two things that would add to 105 degrees. I'm going to choose 60 and 45. First of all, they add up to 105, but they are also things that are on my unit circle. So now I'm following these angle sum identities. This is the version I'm using because I'm dealing with a sine problem. So I'm supposed to take the sine of the first, cosine of the second. And this one is a plus cosine of the first, sine of the second. As I said, some of the values we tend to use this for come up with similar answers, and I'm going to end up that way again. So the sine of 60 is going to be the square root of 3 over 2, cosine of 45, cosine of 60, sine of 45, and I'm supposed to add those up. I get a very similar answer, square root of 6 plus the square root of 2 all over 4. Now I can keep going through this and figuring this out, but there's something to be said for these cofunction identities. For number 7 up here, I could certainly use 30 and 45. They would add to 75. I could maybe do a difference and take 105 that I just came up with and subtract off 45. I could get there. There's other things that I can do. But I'm going to take this one step further, and I'm going to use this cofunction identity idea. The cosine of 75 degrees, according to this, would be the same as the sine of 15 degrees. Because the 15 and the 75 add up to 90. This is all based off of first quadrant. So that means I already have this answer. If I did the sine of 15, and that's the same as the cosine of 75, I'm going to get this very similar looking answer. The square root of 6 minus the square root of 2 all over 4. Now, of course, tangent does different things differently. It has a lot of tangent values in there. It makes it a fraction, but it works the same way. If you have a sum, you work through this formula. If you have a difference, you work through this formula. So they all work very similarly. Sometimes we use the cofunction identity to save us some work. The negative angle identities help with the verify. Our focus, for our purposes, is going to be a lot of the angle difference and the angle sum identities to help us find some of those in between values.